In our first example today, we'd like to take a look at how we can use what we now know about polar molecules and the types of intermolecular forces that they possess to make comparisons, qualitative comparisons, about how strong we expect their physical properties to be, how high we expect their boiling points to be, how high we expect their melting points to be, or in this case, how low we expect their vapor pressures to be. Remember, we talked about vapor pressure on Friday, and we said that vapor pressure and boiling point are inversely related to one another. So vapor pressure describes the partial pressure of a volatile liquid, a liquid going to the gas phase, above the liquid layer at a specific temperature. What this means is that if you have a low normal boiling point, you have a high vapor pressure. If you have a high normal boiling point, you have a low vapor pressure. So we gave an example last time where we showed that at every temperature, water has a relatively low vapor pressure, whereas a less polar molecule like diethyl ether has a much higher vapor pressure, and not surprisingly, the boiling point of water, 100 degrees Celsius at 1 atmosphere pressure, is quite a bit higher than diethyl ether's, about 38 Celsius at 1 atmosphere pressure. So in this problem, we have been given abbreviated Lewis structures for 4 molecules. Based on the abbreviated Lewis structures, we want to identify the types of intermolecular forces that the molecules possess. And then we want to make a prediction about which one has the highest and the lowest vapor pressures based on the strength of their intermolecular forces and their molar mass. So our molecules are ethanol, which is the alcohol found in beer, wine, and spirits. We have ethylene glycol, which is the active component in antifreeze. We have diethyl ether, and we have water. In the electron dot structures that have been shown here, the carbon-hydrogen bonds have been abbreviated, so you just see the number of hydrogens connected to a carbon. So for instance, in ethanol, when you see this first H3C, that's a carbon atom with 3 hydrogens single bonded to it. And the reason the hydrogens are being abbreviated is because in general, with that small electronegativity difference between hydrogen and carbon, if we're thinking about the polarity of the molecule, if we know that there are carbon and hydrogen atoms down here, it doesn't change much about our assessment of the dipole moment for the molecule. So in this case, they're really emphasizing the connection between the carbon atoms and the electronegative atoms to help you more easily visualize which molecules are polar and which are not polar. In the full key for this problem that I've attached below this video, I actually show you the full Lewis structures for these compounds. So if you're having trouble connecting the abbreviated Lewis structure to the three-dimensional shape of the molecule, that's something that we can work on. And in general, if I give you a molecule on a quiz or an exam and I ask you about its polarity, I'll give you the full Lewis structure, not the abbreviated Lewis structure like we're doing here. For those of you moving on to organic chemistry, recognize that for molecules that are largely hydrocarbons, like the organic molecules that we're looking at here, abbreviated Lewis structures are common because most of the molecules are carbon and hydrogen. And what the people who are drawing structures for a problem like this really want to call your attention to is how the carbon atoms are connected to more electronegative elements, like oxygen in this case. So to make our decision about what types of intermolecular forces each molecule has, we need to get an idea of their molecular geometry. So our big strategy here is vapor pressure is inversely related to boiling point. So we're going to do what we've done before and identify the intermolecular forces that each molecule possesses. And the idea is the stronger the intermolecular forces, the higher the boiling point is going to be. Remember that a high boiling point equals a low vapor pressure, so the stronger the intermolecular forces, the lower the vapor pressure is going to be. So we need to take the Lewis structures here and relate them to the three-dimensional structure of the molecule. And that's what I've done in the full key. So I'm not going to redraw the three-dimensional shapes of all these molecules here, but I have linked some materials below the video to help you visualize those better. If you can't immediately see the shape of the molecule based on the Lewis structures that are shown here, that's okay, but it's something you need to continue to work on, potentially with a model kit in front of you. And that's what I include in the full key. Based on our analysis of the molecular geometries of the molecules, we conclude that ethanol is a polar molecule, Ethylene glycol is a polar molecule. Diethyl ether is still a polar molecule, but it is the least polar of the four molecules, and water is a polar molecule. So really all four of our molecules are polar, and we would expect them to have relatively strong intermolecular forces. What we also notice is that in ethanol, we have a carbon bonded to an oxygen that has a hydrogen on it and two lone pairs. In organic chemistry, the presence of this carbon oxygen hydrogen bond with this carbon bonded to an oxygen bonded to a hydrogen with two lone pairs on the oxygen is what makes something an alcohol. So if you see this structural motif, this conjunction of atoms, carbon, oxygen, hydrogen, in an organic molecule, it is an alcohol. So ethanol is an alcohol, ethylene glycol is an alcohol, and water is similar to an alcohol in that we have an oxygen atom with two lone pairs and a hydrogen covalently bound to it. And what we said was that for polar molecules that have this electronegative element, nitrogen, oxygen, or fluorine, with at least one lone pair and a single bond to a hydrogen, these are molecules that are capable of hydrogen bonding. So of our four molecules, ethanol, ethylene glycol, and water, we would also expect to have hydrogen bonding as a significant intermolecular force. So water, ethylene glycol, and ethanol have the full suite of intermolecular forces. They have dispersion forces, they have dipole-dipole forces, and most significantly, they can hydrogen bond. Diethyl ether is polar, but while this oxygen has lone pairs attached to it, the single bonds from the oxygen are to the carbon atoms, not the hydrogen atoms, and diethyl ether cannot form hydrogen bonds to itself. As a result, although diethyl ether is a polar molecule, its intermolecular forces are the weakest of the four molecules that have been shown, and diethyl ether can only participate in dispersion interactions and dipole-dipole interactions. As a result, we would expect that of these four, although diethyl ether is polar, it should have the lowest boiling point and the highest vapor pressures. Based on the molar masses of these compounds, we would be able to take of the remaining compounds, ethanol, ethylene glycol, and water, we would be able to take a stab as to who had the highest boiling point. But deciding among hydrogen bonding compounds which molecule would have the highest boiling point can be tricky because the number of hydrogen bonds that each molecule can form to its partners also matters. And so water actually has a significantly higher boiling point than ethanol does, even though it's a smaller molecule with a lower molecular weight. So really all we can say based on our analysis is that diethyl ether should have the lowest boiling point and should have the highest vapor pressure, which is not nothing. It'd be trickier and beyond the scope of a Gen Chem class to choose between ethanol, ethylene glycol, and water and decide qualitatively which one would have the highest boiling point. But we know kind of instinctively based on data we've seen before that water has a higher boiling point than ethanol, but it's not something that we can predict just by looking at their structures yet. So what we can say for sure is that diethyl ether has the highest vapor pressure at any given temperature of these four molecules.